The first isomorphism theorem is probably the most important theorem that we have in first semester abstract algebra. If phi is a group homomorphism from G to G prime, then we have proven several times that the kernel of phi is a normal subgroup of G. Therefore, G mod the kernel of phi is a factor group, and it is isomorphic to the image of phi. The image of phi is a subgroup of G prime. It may be all of G prime. If the image of phi is equal, note that if the image of phi is all of G prime, then we can say that G mod the kernel of phi is isomorphic to G prime. And this is often the kind of problem we're asked. We're asked to show that G mod one of its normal subgroups is isomorphic to some other group. Well, in that case, we have to find the mapping from G to G prime, show that the subgroup is its kernel, and show that the image of phi is all of G prime. So that's worth writing down. If you are asked to prove that G mod H, some factor group, is isomorphic to G prime, you can do it using the first isomorphism theorem. You need to define a map from G to G prime and show that the map phi is a homomorphism, show that its kernel is the subgroup H, and show that phi is onto. In other words, the image of phi is all of G prime. Then you can conclude that G mod H is isomorphic to G prime. Now, in the last class, Emily asked an important question. She said, well, I thought to show that two groups were isomorphic, you would define a map between this group and this group, and show that that map was a one-to-one onto, in other words, an homomorphism, which is, in other words, an isomorphism. That is the way that we would prove that two groups are isomorphic. But in the case that one of them is a factor group, the first isomorphism theorem just gives us a shortcut, makes it easier. Instead of trying to define an isomorphism between these two groups, we define a homomorphism from G onto G prime and show that its kernel is H. So I'm going to do a couple of these examples. These are all examples that you should be able to do, except for the last one, showing that R mod Z is the unit circle in the complex, isomorphic to the unit circle in the complex plane. I did that in class. I would not put it on the test. But any of these questions here, or something very, very similar to them, could be on test 3. So I'm going to do 2 of them today. In this video, I'm going to do this one and this one. So let's look. Sn mod An is isomorphic to Z2. We did that in class, and you did it in your homework. Similarly, GL2R mod SL2R is isomorphic to R star, the non-zero real numbers under multiplication. We did that in homework and in class, so you should have these. We also did in class that one similar to this, and really, well, they're different. Z mod NZ is isomorphic to Zn. Maybe I'll do that one too. I'll do these 3, but you're responsible to be able to do all of them. Okay, first we'll show that the real numbers, the non-zero real numbers under the operation of multiplication, mod its normal subgroup, this subgroup here, generated by minus 1, of course, is just the little two-element subgroup, 1 and minus 1. It's normal because we're in an abelian group. We want to show that that factor group is isomorphic to the positive reals under multiplication. So we need to define a map from R star. Notice the map has to go from R star onto the positive reals, and then we need to show that the kernel is this little subgroup. So let's define our map. Let's let phi map the non-zero reals to the positive reals by, well, let's see, let's take the absolute value. Phi of x is equal to the absolute value of x. You can see that that's definitely a mapping onto our plus. All positive reals are the absolute value of something. So we don't have to say much there. Let's do phi of xy equals the absolute value of xy, which is the absolute value of x, times the absolute value of y, which is phi of x, phi of y. Therefore, phi is a homomorphism. Phi is onto. Obviously, any positive real number is the absolute value of itself, for example. And so now we need its kernel. The kernel of phi is the set of all numbers that map to the identity in the positive reals under multiplication. The identity is 1. So the kernel of phi will be -1, 1. And that is our little subgroup generated by -1. So once we have that, we're done. We can say that, therefore, by the first isomorphism theorem, R star mod the subgroup generated by -1, that factor group is indeed isomorphic to the positive reals under multiplication. This one we did in class, but I think it's worth doing over because we haven't worked too much with the group of linear functions. Remember, the operation in a group of functions is function composition. So L is the set of all linear functions, which are mappings from the real numbers to the real numbers, of the form ax plus b. And L does not include the functions where a is 0. So that's our group. The operation is function composition. And we want to show that if I'm going to call it k, if k is equal to the set of all these functions where a is 1, so I could just say f sub 1 comma b. All of those for any b in the real numbers. The constant term could be anything, but the coefficient of x is 1 on these functions. Or I could write this as the set of all f such that f of x is equal to x plus b, using a little bit different notation. In other words, this set that we're given is the set of all lines parallel to y equals x. And we're asked to show that L mod k is isomorphic to R star, the set of all non-zero real numbers under multiplication. So in other words, the factor group L mod k has the exact same algebraic characteristics that does R star. So in order to prove this, we're going to need to have a map phi that will map L onto R star, so that R star is the image of phi, and we're going to have to prove that its kernel is, in fact, this set of linear functions with the coefficient of x being 1. So let's define our map. let phi take L to the set of positive real numbers by phi of f sub a comma b will be equal to, well, let's let it be equal to a, the coefficient of x. Why? Well, because 1 is the identity in R star, and this will map all of the functions with coefficient of x equals 1, a equals 1, to the identity, and that's exactly what that's exactly what we want to be our kernel. All right, so let's prove it's a homomorphism. Phi of f sub a comma b circle phi of f sub c comma d. Function composition. That is equal to phi of, and if you take the composition of those two functions, and you should do this on the side, it's equal to f sub ac, that's the coefficient of x, and the constant is ad plus b. Now you make sure that you see why this is true. If you compose these two linear functions, you'll get acx plus ad plus b. And so that was operating inside of L, and now phi takes it to the coefficient of x, which is ac. But that is equal to phi of f sub a comma b phi of f sub c comma d. So we do have phi is a homomorphism. Obviously, phi is onto. The image of phi is all of R star. If you take any real number, let D be in R star. Then phi of, how about f sub d comma 1. Now, there's infinitely many that will map to it, is equal to d. So it's onto, and all we need is the kernel. The kernel of phi will be equal to the set of all f sub a comma b such that phi of f sub a comma b is equal to 1, the identity in R star. Well, that's just when a is equal to 1. So it's equal to the set of all f sub 1 comma b, where b can be any real number. So the kernel is equal to k. This is k, the set that we defined at the beginning of the problem. So we can conclude, therefore, L mod the kernel k is isomorphic to the image of phi, which is, in this case, all of R star. So just think how much this simplifies the way that algebraists can look at a factor group. The set of linear functions modding out the ones parallel to the line y equals x. It's hard to even think about them, about that factor group, this infinite set of cosets of functions. But it's really easy to think about R star. So once you prove that, you can think about very complex groups, factor groups, in terms of their image, their homomorphic images. The first isomorphism theorem can be used to determine all homomorphic images of a group G. If we know the normal subgroups of a group, then we know that the only homomorphic images of the group will be those that are isomorphic to G mod its normal subgroups. Now, instead of doing D4, I'm going to do a simpler example here. Let's not do D4. Let's find all the homomorphic images of Z10, and then I'll do D4. So we want to find all the homomorphic images, all of the groups that could be the images of a homomorphism from Z10. Well, we need to know what its normal subgroups are. The normal let's say Z10 has normal subgroups. They're all normal because it's abelian of indices. The divisors of 10. 1, 2, 5, and 10. Now, the subgroup of index 1 would just be Z10, is a normal subgroup of Z10. The normal subgroup of index 2 would be this one, generated by 2. We would get, we know we're going to get 0, 2, 4, 6, 8, and 0. The one of index 5 would be the subgroup generated by 5. That would give us the subgroup 0 and 5. It has 5 cosets, and of course the one of index 10 that only has one coset is just the little subgroup containing the identity. So remember, the index is the number of cosets, or the order of the factor group. So the one of index 1 is Z10. Index 2, in other words, there's 2 cosets of that subgroup. There's 5 cosets of this one, and 10 cosets of the little trivial subgroup containing only the identity. So we know that Z10 mod Z10 is isomorphic to the little trivial subgroup, and that Z10 mod the identity is isomorphic to Z10. So both the identity, I'll just say E, meaning any, this is a homomorphic image, and of course Z10 itself is a homomorphic image. So those are trivial, but let's see about this one and this one. Okay, Z10 mod the subgroup generated by 2 is isomorphic to, well, it has 2 cosets. So there's only one group of order 2, and it is the little abelian group, and we'll just call it Z2. And if you spend a little time with this, you'll see that Z10 mod the subgroup generated by 5, which has 2 elements in the subgroup, therefore index 5. This is isomorphic to a group of order 5. Well, there's only one group of order 5. It's prime. It's the cyclic group of order 5. And we might as well just call it Z5. So we have 4 homomorphic images of Z10. You could have a homomorphism on 2. The image of a homomorphism could just be the identity. The image of a homomorphism could be a group isomorphic to Z10, or the image of a homomorphism could be Z2, and the image of a homomorphism could be Z5. So this means that all of the factor groups of Z10 are isomorphic to one of those 4 groups. The only 2 of interest here that aren't obvious would be the cyclic group of order 2 and the cyclic group of order 5. Let me say that one more time. All factor groups of Z10 are isomorphic to, are cyclic of order 2 or cyclic of order 5. So now let's look at the dihedral group. D4. We want to find all homomorphic images. Find all homomorphic images. Well, to do that, we need to know the normal subgroups of D4. And, this would take you some time. You have to look at this and figure it out yourself. The normal subgroups of D4 are the following. Well, of course, the identity. And, of course, D4 itself, the two obvious ones. The other normal subgroups, well, the center of D4 is this one, E R squared. In other words, the little cyclic subgroup generated by R squared. That's equal to the center of D4, and we know that the center of a group is a normal subgroup. And by the way, you should be able to prove that. That's in our handout. Handout 4. Another normal subgroup is the one generated by R, which is the identity R, R squared, and R cubed. And we have two other normal subgroups that have 4 elements in them. One is generated by both R squared and H. Take all possible powers and products of the two elements, and we get E, R squared. We get H squared is the identity, and we get H, R squared. And that is a normal subgroup. The other normal subgroup of order 4 is generated by R squared and HR. Here we get the identity R squared, HR, and HR cubed. These are all the normal subgroups of D4. And so the only homomorphic images, the only groups that you could make a homomorphism from D4 onto them, are isomorphic to the factor groups of D4 using these normal subgroups. So let's look at the index of these subgroups. Well, of course, this has index 8. There's 8 cosets of the identity, and D4 has index 1. But here we have 2 elements in the subgroup, so the index will be 8 divided by 2, index 4. And all of these are 4 element, so these all have index 2. There are 2 cosets. Well, if there's only 2 cosets, that means that D4 mod R is isomorphic to D4 mod R squared H is isomorphic to D4 mod R squared HR, that subgroup. And they're all isomorphic to the only 2 element subgroup there is, the little cyclic subgroup, and we'll just call it Z2. So we have homomorphic images. It is possible to make homomorphisms from D4 onto Z2. And the one of index 2, well, just a sec. The center of the group, let's call it, let's just call it H so I can use something other than this, E and R squared. We know the index is 4. In other words, D4 mod H, the order of D4 mod H is 4. So it could be isomorphic to, we know there's 2 groups of order 4. So the question is, in our minds, is this isomorphic to, well, is it isomorphic to the Klein 4 group, or is it isomorphic to Z4? We don't know. But instead of writing out a group table for this factor group, what's the difference between V and Z4? The Klein 4 group, every element squared is the identity. So let's just look at some of the, let's just take this here and let's take R, we have RH, that would give us, let's see, that would give us R and R cubed. And we have our squared h is h, our cubed h is, so we have h, which would give us the coset h and hr squared. And we have hrh, which would give us hr and hr, let's see, hr, r squared, hr cubed. And then, of course, we have h itself. So these are the elements of the factor group. And I'm just going to see if when we square them, we get all of them, we get the identity. If we take RH, we get, using our definition of star, I didn't write star there, but we have r squared h, which is equal to h. So this one has order 2. Let's take HH, HH. We get h squared h squared is the identity. This one also has order 2, and you don't even have to try the third one, because we know that that if these 3 elements all squared give the identity, this one is 2. Z4 only has 1 element of order 2. So we know that D4 mod H is isomorphic to the Klein 4 group. So all homomorphic images is either isomorphic to D4, or just the identity, or the Klein 4 group, or just Z2. These are all homomorphic images of the group, the dihedral group D4.